And as a brief introduction of our speaker, Professor Anthony J. Leggett is a Nobel laureate in physics and an internationally acclaimed theoretical physicist, widely recognized for his profound contributions to the field of condensed matter physics. He currently holds the John D. and Catherine T. MacArthur Chair at the University of Illinois Urbana-Champaign, UIUC, where he has been a central figure in advancing the theoretical framework of quantum mechanics as it applies to complex many-body systems. Professor Leggett has authored numerous high-impact publications and delivered invited lectures across the globe. In recognition to his extraordinary scientific achievements, he has received a wide array of international honors, including his knighthood by Queen Elizabeth II in 2004 for services to physics. He is a fellow of the American Physical Society, the American Academy of Arts and Sciences, and a foreign member of the Russian Academy of Sciences, known for his clear and insightful communication of complex ideas. Professor Leggett remains a prominent voice in contemporary physics, influencing both theoretical research and philosophical discourse on quantum science. His legacy continues to shape the trajectory of quantum physics and inspire new generations of scientists.
Thank you. Good evening, everyone. I would like to start this talk by showing you a really rather simple sentence. Yeah. So let me just read it in case you can't. The sentence simply reads, had I woken up 5 minutes earlier this morning, I would have caught the 8 o'clock bus. A rather simple English sentence. I would like you, all of you please, since your native language is often not English, could you just, first of all, try to translate this sentence into your own language, and then just check that it makes sense or not. And I would like to ask, is there anyone who feels that they can't translate it or that this sentence does not make any sense? Well, so hopefully the answer is everyone finds it intelligible. Okay, we'll see in a few minutes why this is relevant. So my talk is about realism in physics, and because that raises the question, what do we or can we mean by realism? Well, philosophers, of course, have been discussing the question of what is and is not real for a long time, and they've argued, for example, about whether the human mind is real, whether the number 5 is real, whether moral facts are real. These questions are a bit difficult to resolve from the point of view of physics. They don't really seem to have much to do with physics. On the other hand, you can also ask questions, say, about things like atoms or electrons. Please stay. Yeah, okay. No, please stay with this slide. Yes, that's fine. Good. Yes. So the question is, in what sense can physics, as such, say something about realism? And as I said, to answer that question, we have to start with some kind of definition of realism. And here is my proposed definition. It's in the box. At any given time, the world has a definite value of any property which may be measured on it, irrespective of whether that property actually is measured or not. To make that proposition possibly experimentally testable, we need to extend it to finite parts of the world. And so let me then ask the question, which is actually irrespective of the universal validity or not of quantum mechanics. What can we say about this proposition, the proposition in the box, directly from experiment? And that really is the question that I'm going to try to talk about in this talk. As I say, it's strictly speaking not about quantum mechanics, but it is, as you'll see, rather closely related to it. Okay, next slide, please. Okay, well, to discuss realism in physics, let's start with the very simplest case, which is a two-state system. For example, a microscopic example might be photon polarization. Suppose we have a situation in which we have a single photon, which is heralded. That is, we know that the photon is there, right? And this photon is incident on a polarizer with a transmission axis, say, parallel to A, the vector A. And if it passes the polarizer, then it enters a detector, and the detector will then trigger various macroscopic events. For example, it can ring a bell or flash a light or print out some kind of tape to show that it's been activated. If, on the other hand, the photon does not pass the polarizer, then it'll go into a different detector, which is labeled N for no, as distinct from this one, which is Y for yes. Again, something in that detector will happen. There will be a bell ring or a light flash or a computer tape printed out. And so this rather simple experimental situation, we can say that we basically posed a question to the photon: are you polarized along A or not? And if the answer is yes, if the Y detector clicks, the answer is yes. If the N detector clicks, the answer is no. Now, it seems to be an experimental fact that for each photon, either the counter Y clicks and the counter N does not, or vice versa. The counter N clicks and Y does not. So as I say, the natural paraphrase is to say that when asked, each photon answers either yes, or that is A equals +1, or no, A equals -1. Now, I'll just use those expressions, A equals +1 or A equals -1, to stand for the answers yes or no, respectively. Well, so far so good. But what happens if we don't answer the question? In other words, we don't have a measuring device. So we can imagine, we just have a single heralded photon. That is, we know the photon is there, but we are not doing anything to measure its polarization. So next slide, please. So we could do this in the following way. We can arrange that we have this single heralded photon, and it is incident on some kind of switch. And the switch may direct the photon into a measuring apparatus, which is the type that I mentioned previously, or it may direct it elsewhere. And so now we ask the question, suppose that a given photon is directed elsewhere, then does it have a definite value of A? In other words, does it definitely have an answer yes or no to the question which we might have asked it but didn't? And then we have to raise the question, what does this question actually mean? Next slide, please. Well, a way of answering this question, at least implicitly, was devised effectively by John Bell many years ago, and has been implemented in a large sequence of experiments over the last 60 years or so. And the experiments in question, which I suspect many of you are familiar with, are the so-called EPR Bell experiments, Einstein-Podolsky, Rosen, and Bell. And here is an idealized account of those experiments. You start with some kind of atomic source, S, in this picture. And that source emits 2 photons back to back. And one of the photons is switched into a counter, C1, at the right-hand side of the figure. And the function of that counter, C1, is to switch this photon into either a counter, which will measure A, that's given in the diagram below here, or a similar device which will measure A prime. That is, it will measure the projection of the photon polarization on a different axis from A. So this is the basic setup of the EPR Bell experiments. Each of the photons is submitted to a counter, to a switch, which can direct it into a counter, or one of 2 counters, which may measure alternative things. A or A prime for the right-hand photon, and B or B prime for the left-hand photon. And then there is a famous inequality proved by Claus Holt, Shimoni and others many years ago, which says that all so-called objective local theories, I'll come to that in a minute, all objective local theories satisfy a particular constraint on the correlations between the value of A, which we measure, and the value of B, which we measure. So the quantities here are the experimental correlations of the quantity A measured on the right-hand photon, A or A prime, and the quantity B or B prime measured on the left-hand one. This is a famous inequality, and one of the reasons it's famous is that the predictions of quantum mechanics actually violate that inequality, the one marked in red here. But it's equally important for my present purposes that the inequality is actually violated by the experimental data. I'll say a bit more in detail about that in a minute. Now, notice, incidentally, that for purposes of refuting objective local theories, in other words, of refuting this inequality, we don't have to have a single atomic source which emits the photons. We can generate the photons in whatever way we care to, and in fact, in some experiments, they have been generated more indirectly. Next slide, please. Now, what do these experiments, these idealized EPR Bell experiments, show? Well, as I say, they show that the class of objective local theories is violated. What is this class? Well, objective local theories, or OLTs, are defined by the conjunction of 3 postulates. The first is what we might call realism itself. That is, as in my earlier slide, the postulate of realism is that physical systems have definite properties whether or not these properties are observed. But then you do need to add a couple of other properties. The next one is locality, namely that no causal influence can propagate with a velocity greater than the speed of light. And the last one, which is often not mentioned in detail in discussions of this experiment, the absence of retrocausality. I sometimes call that induction, but it may not be a terribly good name for it. And the postulate is that the future cannot affect the present or the past. Or in other words, that ensembles are characterized only by their initial or preparation conditions, and not by whatever may be done to them subsequently. So you can regard then these three postulates, the conjunction of these three postulates, as defining an objective local theory. Next slide, please. Yeah. Let's just go through a very simple, almost trivial proof of the CHSH inequality. Well, first of all, by postulate number one, which remember was realism or objectivity, for any given pair of photons, the quantities A, B, A prime, B prime, all exist and can take values plus or minus one. And that is true whether or not these values are actually measured. Second step is that by postulates 2 and 3, the value of A is independent of whether it is B or B prime, which is measured at the distant measurement station, and of course vice versa. The value of B is independent of whether it's A or A prime that's measured. And those two postulates then imply that for any given pair of photons, the quantities, that is the products of these quantities, AB, AB prime, A prime B, A prime B prime, each of these four quantities exists. And the crucial point is that A takes the same value, either plus or minus 1, in AB and in AB prime. That may seem sort of trivial, but we do need to state it explicitly. And so, once you've convinced yourself that this postulate step number 3 is right, then you can just do a bit of grade school algebra and find that for any given pair of photons, the quantity written in point 4, AB plus A prime B plus AB prime minus A prime B prime, is less than or equal to 2. That's, as I say, that's a trivial piece of algebra, which can just be by exhausting different possibilities. And therefore, next step is that when measured on the same ensemble, the expectation values also ought to satisfy this inequality. In other words, we get the inequality at point pi. Now, unfortunately, that's not quite enough because, strictly speaking, you should write the experimental measured correlations with a subscript which tells you what it is you're actually measuring in that particular run on the experiment. However, by postulate number 3, the properties of the ensembles only depend on their initial condition and not on what you choose to measure them subsequently. And therefore, the correlation AB measured on the ensemble, in which A and B were measured, is the same as the value of AB for the for different ensemble on which A and B prime are measured. And having convinced yourself of that, then you can write that the expectation value of AV is identical to the value which was actually measured in the experimental run in which A and B were measured. That is an important step in the proof, but as I say, it is guaranteed by point 3. And so as a result of that step, you can finally write down that the experimental values of the correlations, AB, A prime B, AB prime, and A prime B prime, satisfy the lost inequality on this side, which is precisely the CHSH inequality which we're trying to prove. So indeed, then all theories satisfying the conditions of the objective local class have to satisfy the CHSH inequality. Next slide, please. So, as I say, that's the case, and nevertheless, the experiments come out against that result. In other words, the CHSH inequality is violated. And therefore, at least one of the postulates defining an objective local theory must fail. Are we going to question locality? Are we going to question induction? Or are we going to question realism? Well, that's a topic which has been discussed rather intensively for the 60 years or so since the initial experiments were done. Let me comment at this point on one particular issue which arises in this connection. As we've seen, the assumption of number one, the assumption of realism is usually made part of the definition of an objective local theory. But is it actually needed in order to derive the CHSH inequality? If the answer is no, then rejection of that postulate won't actually help. We'd still need to reject either locality or induction or both. Now, in a rather provocative paper some years ago, Nicolas Gissin claimed that the answer to this question is no. In other words, it's enough to assume that we don't need to make a postulate of realism. All we know to do is to assume that any given state lambda, where lambda could be, but need not be a hidden variable label, but for any given state labeled by lambda, we have the locality relations, namely that the probability of getting A for a state lambda on which A and B are measured is simply the probability of getting A. In other words, the setting of B is irrelevant. Similarly, the setting of A is irrelevant to the value of B. If that is the case, then you can write this inequality, which relates the correlations of A and B to the individual measured values. And at first sight, at least, and Gissin makes this point, these assumptions are sufficient to permit derivation of the CHSH inequality. So, according to this argument, one would not need to invoke the postulate of realism. And I thought there would really be no great reason for me giving it to report. Next slide, please. How does the snag with Gisan's argument. Suppose the distribution of values of lambda is given by this formula here. In other words, I can have various discrete values of lambda sub I, and each one of those occurs with a given probability. Then the probability of A and B, given that you measure A and B, is given by this expression here. But there is a problem here, because if the number of values of lambda which are available is greater than the number of trials, then the pairs AB, the pairs of values AB and AB prime, they're never actually measured for the same value lambda j, lambda. And therefore, the derivation of the CH and SH inequality fails. That's true, provided this inequality, number of values of lambda, much greater than the number of experiments, provided that is satisfied. And that's always true if lambda is a continuous variable. If that's true, then Gisan's derivation fails. And so we do, after all, need assumption of 1. And in turn, that means that if we, following the experimental refutation of the CHSH inequality, if we want to keep assumptions 2, which is locality, and 3, which is induction, we can do so, but we then must reject assumption 1, which is realism. So that is why I don't think that the argument given by Gisan is actually convincing in this respect. I think one does need to have that to make an explicit postulate of realism. Next slide, please. Well, as I say, the CHSH inequality has been tested for the last 60 years in a whole series of experiments, probably by now hundreds of them. But before 2015, there were a number of obvious loopholes in the experiments. First loophole was whether the locality proposition was actually satisfied in the real experiments. And that would not be so if the event of, say, switching at counter C1 is not space-like separated from the detection in the measuring apparatus NP. In other words, information could be conveyed subliminally from the choice of what to measure at the right hand end of the laboratory to the detection event at the left hand end of the laboratory, and vice versa. That's one loophole. A second loophole is the so-called freedom of choice one. The switching at C1 may not in fact be random. It may in some way be influenced by the experimental's wishes or something like that. And the third loophole, which was for many years the most emphasized and important one, is the detection loophole. If the counters were not 100% efficient, then the detected particles might not be representative of the sample as a whole. And until the experiments done in November of 2015, many experiments had blocked one or two of these three loopholes simultaneously, but no experiment had blocked all three of them simultaneously. And the obvious question is, why not? Well, the blocking of loophole number one, that is locality, requires a space-like separation of the switching at C1 and the detector in M2. And similarly, the blocking of loophole number two requires a space-like separation of the switching at C1 and the emission at the source, or the equivalent. And it's easy to satisfy those two conditions for photons, but very difficult to satisfy it, for example, for atoms. On the other hand, the blocking of loophole 3 requires a detection efficiency which is greater than 82.8%. And that high detection efficiency is easy for atoms, but difficult for photons. So in other words, it's difficult to find a system in which both of these loopholes are simultaneously blocked. But you do that. If you don't do it, then you can't exclude a giant conspiracy of nature, in which somehow nature managed to get around the constraints implicit in the CHSH inequality. And for many years, that was the holy grail of experimental optics. And as we'll see, it was in fact resolved in a group of experiments carried out in December of 2015. Next slide, please. Yeah. Well, in fact, what some of the experiments conducted in 2015 did was not to actually test the CHSH equality directly, but rather a generalization of it due a few years later to Eberhard. In this generalization of the inequality, you still have the choice of you still have a switching of photon on the right, say, into counter A or counter A prime, but now counter A is rather more primitive. Counter A simply consists of a polarizer here, followed by what we call the yes detector. In other words, if the photon passes the polarizer, then it gets registered in the Y detector. But if it gets rejected by the polarizer, then it does not enter a detector at all. You remember that in the earlier diagrams, we actually had a detector in this arm here. But now we don't. We just allow that photon to go off harmlessly. In other words, you don't mind whether the non-detected particles had a polarization which is actually perpendicular to A, or they were simply not detected because of the inefficiency of the counter. And with that, you can, the proof is now rather more tricky, but you can actually prove a generalization of the CHS inequality, which is this inequality which is written down on this slide. And we're here, for example, the notation P plus 0 measured with A and B is means the probability that particles switched into detectors A and B. Detector A fires and detector B does not. And you don't have to worry about why detector B does not fire. Now, this inequality is valid, it's a general inequality, valid independently of the detection efficiency, but the predictions of quantum mechanics violated only if the efficiency is greater than 67%. So you still need, in order to use the Eberhard inequality, you still need a fairly high efficiency of your detectors. Next slide, please. So this is just a brief list of the EPR-Bell experiments, which were conducted in November or December of 2015 and have become, in some sense, a classic of the subject. There was an experiment in Delft which used electron spins at a distance of 1.3 kilometers. That one did test the CHSH inequality itself, and they found a value of the quantity K-2, which is 0.42, enough to definitively violate it. And the quoted significance statistically was this quantity here. So this is the probability you could have got this result more or less by accident. The second experiment was done at NIST in Boulder, Colorado. They used photons with distances of 185 meters, tested the Eberhard inequality. They got a large value of the significant quantity, and the significance is something like 10⁻³. Finally, an experiment conducted at the Quantum Institute in Vienna was again on photon polarization with a smaller distance involved, and they used the Eberhard inequality, and they got a value of the significant quantity, which is definitely non-zero, and they quote a significance of less than 10 to the minus 20, which seems actually a bit difficult to believe. I mean, in real life, it's very difficult to get significance that low. So one might perhaps put a question mark next to that particular figure here. But anyway, just summing up these experiments, it looks as if all three of the experiments conducted at the end of 2015 did show a violation of either CHSH or the Eberhard generalization of it, which was significant and highly quantitative. So that I think, at least at the time, was looked at as a major milestone in the experimental test of local realism. So do these experiments mean that local realism is dead? Well, unfortunately not quite, because there's still one or two remaining loopholes, some of which were noted by the authors of these experiments. The first loophole is superdeterminism, the idea that, for example, the switching events in the experiments are not really random, but they were determined by some conditions at the origin of the universe or something like that. That doesn't seem terribly easy to test experimentally. The second surviving loophole is retrocausality, meaning that in some sense, the future can affect the present or the past. That's in some sense, a rather wild-looking hypothesis, but again, it's not easy to see how you would actually test that. The final loophole is, I think, more interesting. It's a loophole which is sometimes in the literature called collapse locality, and that is based on the consideration that you don't actually know at what point in the measurement process a definite outcome was realized. I mean, was a definite outcome realized when the photon in question passed or failed to pass polarizer? Well, That would be difficult to maintain because, after all, there are different classes of experiments in which the transmitted and reflected photons can actually interfere. Then was the definite outcome realized when the photon, having, say, passed the polarizer, triggered, entered the photon multiplier and triggered an event? Well, again, that's not what quantum mechanics says. Was it realized when a macroscopic bell was rung or a flash occurred or whatever? Yeah, well, quantum mechanics doesn't say anything about the special nature of macroscopic events. And that then leads to the question, can we actually tell experimentally at what point in the measurement process a definite outcome is realized? Well, we're not going to be able to do it from the Bell EPR experiments, but other experiments of a different kind which can say something about this. And that's the question to which the last few minutes of my talk would be devoted. Next slide, please. Okay, so now let's consider a class of experiments of a rather different kind, which I'll call experiments on macroscopic quantum coherence, or MQC. Imagine that we have a system which has available to it two different macroscopically distinct states, which I'll call plus or minus. And suppose we start it, let us say, from a situation in which it's known to be in the plus state here, allow it to propagate as it wants to, and then actually measure at the final time, we will measure which of these two states it actually ends up in. Well, what would be a real-life example of this? Well, one example which has been widely used is the example of a so-called flux qubit. A flux qubit is a superconducting ring which is interrupted by a single Josephson junction here. And then it turns out that with this rather simple device, you actually have two macroscopically distinct ground states corresponding to a current circulating anti-clockwise in this case, or clockwise in this case. And so you can actually label these with the variables q plus 1 or q plus minus 1. Now, the question we would like to try to answer is the following. At this intermediate stage of the experiment, at a time in t sub int intermediate, is the system in a definite one of these two states, or is it in some kind of quantum superposition of these states? Well, in the experiments we've done prior to December of 2016, one could say that if the raw data were interpreted in quantum mechanical terms, then you had to infer from the results of the experiments that at the intermediate stage it was in a quantum superposition and therefore not a mixture of the macroscopically distinct states plus and minus. Incidentally, how macroscopically distinct are these states? That's a matter which has been discussed in some detail in the literature, and clearly depends what you mean by macroscopically, but I would claim that by any reasonable common sense definition, the two states of the squid here are indeed macroscopically distinct. We could discuss that if anyone's interested. Okay, so that was the case until December of 2016. What about later than that? Next slide, please. Okay. Well, in order to actually make any definitive statement, we obviously have to define what we mean by a macro-realistic theory. And a possible definition is by the conjunction of three postulates. The first just being macro-realism per se. In other words, whether or not we choose to observe it, Q of t at any given time is either +1 or -1. The second condition, just as in the EPR-Bell experiment, is the absence of retrocausality. The past can affect the present and the future, not vice versa. And the third is a postulate which has to be made specially for this experiment, which substitutes for the condition of locality in the CHSH inequality. We can't use locality in this case because the distances at times involved are macroscopic, and so you don't have the usual locality provision. Instead, we invoke this postulate of non-invasive measurability, which means that we can set up a measuring device in such a way that if Q is measured to be +1, then we say, well, the system may have interacted with the measuring apparatus, so we throw away that run of the experiment. However, if the measuring apparatus does not register, then we can say, well, in that case, there could have been no interaction between it and the system. And so, if indeed it didn't register, in other words, Q is -1, then we can keep that data point. And it turns out that from this kind of negative result measurement, we can in fact obtain all the statistics we need to. Now, the postulate of non-invasive measurability, saying that if you get a negative result, you have not affected the state of the system, that can't be explicitly tested. We can make it plausible by an ancillary experiment to test, for example, whether when QT is known to be +1, a non-invasive or supposedly non-invasive measurement doesn't affect the subsequent statistics. However, for this approach to work, all the measurements do have to be projective or known. Now, before December of 2016, there had been a number of experiments along these general lines, but they'd used weak measurement techniques, and so were not satisfactory from this point of view. Moreover, the states in question were not reasonably, anything we could call reasonably macroscopically distinct. Next slide, please. This situation was changed by an experiment conducted at NTT in Japan in December of 2000, or reported in December of 2016. And for the sake of full disclosure, I should point out that I was actually a co-author on this paper, although my role was minor. And what the NTT experiment did was, rather than measuring two time correlations, it rather checked directly how far a measurement, which was not necessarily non-invasive, at T2 affects the value of Q at time T3. In other words, how it affects the results, first of all, for different macroscopically distinct states, and secondly, for their possible quantum superposition. So that gets a little complicated in implementation and so forth. You can define for any state at time t equal to Q3, you define the difference between the value of Q3 measured with an uninspected outcome, and the value if no measurement at all was made. And so you can do an ancillary test. You can start the system known to be in the plus state. You can then choose either to make an ideal negative result measurement on it, or to do nothing. And you could compare the results for the final state, depending on whether you did or did not make a negative result measurement. Similarly, if you started off in the minus state, it is the same. So you can independently check, or at least prima facie, you can independently check that whether or not making a negative result measurement did affect the final outcome. Next slide, please. Having done that, you could go and do the main experiment where you prepare your system in a state where quantum mechanics says that the intermediate state has to be some kind of quantum superposition. And again, you can define the difference between what happens when it is or is not measured. And in this way, you can actually prove a macro-realistic inequality, namely that this measurable quantity here is greater than 0. Well, this experiment was done at NTT in December of 2006, or reported in December of 2016. The experimental value was certainly negative and reasonably substantial. And it turns out that it violates the macro-realistic prediction by more than 84 standard deviations. So it is statistically very significant. So it seems that realism is refuted at both the microscopic and possibly at a possible macroscopic level. The question is, what does that actually mean? When you say it is not the case that the system is in a definite state, what does that is mean? There's a very famous quote from a totally different realm of human experience, namely politics, which is, it depends what the meaning of is. And indeed, that's true here, more realistically than politics. If you're going to say you've refuted realism, you've got to say more clearly what realism actually is. What do you mean by that? Next slide, please. Yeah. Well, let's look at it this way. Imagine a situation where you have a single held photon moves into a switch which may or may not switch it into an apparatus which will measure the polarization. Suppose, in fact, a particular photon is directed elsewhere. What does it mean then to ask, does it have a definite value of A? In the possible quasi-operational definitions, the following. Suppose the photon had been switched into a measuring device. Then there are two statements one can make. Proposition 1 at first sight looks rather innocent. It looks like a truism. Under those conditions, it's a fact that either counter Y would have clicked, in other words, A equals +1, or counter M would have clicked, that is, A equals -1. That's one proposition. As I say, that looks, at first sight at least, like a truism. Proposition 2 is a bit more subtle. It's the proposition of MCFD, macroscopic counterfactual definiteness. And that says that either it is a fact that counter Y would have clicked, that is, that A equals +1, or it's a fact that counter N would have clicked, namely A equals -1. And so we can try tentatively at least to identify realism with proposition number 2, which is not trivial and does have consequences. Next slide, please. So that then gives rise to the general question, or more general question, do counterfactual statements have truth values? Well, common sense and the legal system and so on and so forth do indeed assume so. But as to common sense, we had the example of the catching or not catching the bus earlier on in this lecture. In the legal system, for example, the prosecuting counsel may tell the jury, had the accused not pushed his victim down the stairs, she would still be alive today. Again, a standard counterfactual statement. The legal system depends heavily on such counterfactual statements being meaningful. So what is MEA? Well, a well-known philosophical attack on this point was given by the philosopher David Lewis in his book Counterfactuals. It's actually the first paragraph of this book. And he says the following. If kangaroos had no tails, they would topple over. Quote, seems to me something like this. In any possible state of affairs in which kangaroos have no tails, and which resembles our actual state of affairs as much as kangaroos have no tails permitted to, the kangaroos topple over. That, of course, is a rather brief statement and needs to be amplified, as indeed Lewis does, by a whole chapter's worth of discussion. But the question is it the case? Can we apply this to physics? Is it the case that in any experiment in which everything else is the same, but we measure A rather than A prime, we always get, say, the same result? That is, we can do any number of experiments on which everything else is the same, and it always will yield a single value of A, as say +1. Well, alas, no, it is not the case. And moreover, the NTT experiment shows that's not simply application of a microscopic indeterminacy, it's still true even at a macroscopic level. That in turn raises the question, is there any meaning to a statement of determinacy in the absence of determinism? And that's a question which I think has not been discussed a lot in the literature, but I think is rather well worth discussing. I've tried to make a start on it, at least in a recent paper. But either way, putting that question aside for a moment, it seems to turn out that from this series of experiments done on both microscopic and macroscopic systems over the last 20 years or so, we may eventually simply have to conclude, last slide please, even at the everyday level, there really is no such thing as would have. Simply counterfactual statements simply do not have truth values. And if we really start taking this seriously, then eventually we're going to have to apply it not just to physics, but to more complicated things. And eventually we're going to end up, for example, at the legal system and realize that the statement often made in court cases about what would have happened are really just meaningless. So if that's true, I think it's really rather worrying for our views of the world as a whole. It shows that these apparently very detailed and very microscopic experiments on single photons or single atoms do have, in the end, implications for our view of nature at the level of everyday life. And that's really the message which I would like to try to get across in this lecture. Thank you.
Thank you so much, Professor. And with your permission, may we proceed to the questions, please? We have a couple of questions from our online and offline audience. So the first question is, with regard to retrocausality, do you think the delayed choice quantum eraser experiment shows retrocausality without violating locality?
Do I think that the recent delayed choice experiments do what?
The question is,
Yeah.
Uh, uh, the delayed choice quantum eraser experiment, does it show retrocausality without violating locality?
Well, yes, I think it does, but I'm not quite clear that's relevant to the subject of realism. Yeah. I think the delayed choice experiments are a particular example of an extension of the CHF inequality, which yeah, I mean these experiments presumably are consistent with the predictions of quantum mechanics being right. We know that in the original CHSH experiments, the predictions of quantum mechanics did work out, and we further know that in the original experiments they violate realism. So I would say that the delayed choice experiments do at least prima facie violate realism. Whether they violate whether they establish causality, I think is much more dubious. I would say they do not actually establish causality, but again, one would need to give a rather explicit definition of what causality consists of in that case. Now, I'm afraid, to be quite honest, I'm afraid that I can't do this completely in my head. So I think the honest answer would be, I don't really know. I'd have to think more about it.
Okay. Thank you, Professor. And the last question. In the context of Wigner's friend, where an observer inside a lab sees a definite outcome while an external observer still sees a superposition, how can realism, which demands a single observer independent reality, account for the contradiction? By Shravan Kumar.
Well, I don't think it can. I mean, I think that the Wigner's friend paradox is a paradox by any criterion. On the other hand, you do have to be careful with it, because after all, the Wigner's friend paradox, at least as far as I know, is entirely a theorist's construct at the moment. No one has actually done that experiment, and I think it would take an extraordinarily sophisticated experimental apparatus to do either the Wigner's friend, the original proposed Wigner's friend experiment, or even anything reasonably close to it. So we aren't actually in the same experimental situation by any means as we are with the microscopic P.R. experiments. Yeah.
Yes, Professor.
But
Thank you.
on the theoretical front, yes, I think there would be a real paradox there if, in fact, the behavior is as quantum mechanics apparently predicts.
Yeah. Yes, Professor. Thank you. And we have a short question, and we request crisp answer for this question by Professor Dipankar Home, a retired senior scientist, Department of Physics. So,
well, yes.
Yes, please.
Hello, Tony. Nice to see you give a talk in Calcutta, and after a long time, and hope to again have you in Calcutta. We had you so many times. And so it is wonderful on 100 years of quantum mechanics conference in Calcutta. You are giving talk, although online anyway. So now I have two comments or questions. One is that macroscopic counterfactual definiteness. So the conclusion seems to be that this is refuted by the experiments concerning this macro-realism experiments.
Yes,
Yes.
I think that would be a fair statement. at least as MCFD, as I and some of my colleagues would actually define MCFD. Yes, I think that is a correct statement.
So it is so now from the Bell inequality perspective, since Bell inequality is also derivable from counterfactual definiteness, so you seem to distinguish between counterfactual definiteness as applied to microscopic or macroscopic level. So for the macroscopic counterfactual definiteness for this macro-realism experiments, it is definitely refuted. For the Bell experiments, you have it in conjunction with the locality condition. No, so that's why.
Well, yes. I think the situation is sort of roughly parallel in the sense that that what is refuted in the NTT experiments is a concept of macroscopic counterfactual definiteness, which is not simply the statement that macroscopic objects are always in definite macroscopic states. It's accompanied by certain statements about non-invasive measurement and the direction of time. So I think in some sense the ancillary assumptions one has to make in the two cases are somewhat parallel. They're not the same, but they are, I think, of a similar nature.
Okay. And one question that suppose after all these experiments on macro quantum, macro realism and macro at the macroscopic level are performed to test superpositions, if all the experiments continue to vindicate quantum superposition at the macro level, given the existence of the quantum measurement problem, what would be your position then? I know many of us like you would like to believe there would be a breakdown, life will be more exciting. But if it turns out the counterfactual question, you may say, then what would be your position? That then here is the quantum measurement problem. What do we do about it? Quantum superposition is all the way valid. What would be the best solution approach?
Yeah, so if all experiments for the next 100 years or 200 years or whatever continue to verify the predictions of quantum mechanics at the microscopic and also at the macroscopic level, I think the only way I can come to terms with this is to take the view of quantum mechanics, which one can call it extreme, if you like, extreme statistical position. It was formulated by Valentine in a rather well-known paper 50 years ago or so, basically says that the only function of the quantum organism is to provide a calculus for calculating the probability of outcome of various directly observed effects. And that all of them should really talk about is this reoccurrence or not of these events at a directly observable level, say the flashing of a light or the ringing of a bell or whatever. And one should simply not try to give any realistic description of what happens at a lower level. In other words, you have the formulas of quantum mechanics, which is beautiful and very good for predictions. You should just not try to interpret it. Crudely speaking, I think this is the sort of view which in some of his writings, at least, the philosopher Hans Reichenbach gave quite many decades ago now. You just don't talk about anything which goes on below the level of direct human observation, or if you do insist on talking about it, don't expect it to make the kind of common sense that we expect in ordinary life.
Okay, thank you.
Yes. Thank you so much, Professor. We are very inspired and we are very grateful for all the information you have shared on the realism and the physical world. And we are hoping to have many more future talks with you. And thank you very much.
Thank you for your attention.